with our fourth lecture on thermodynamics. In our previous classes, we have discussed about the thermodynamic state functions and how these specific terms are defined. We have also got to know about the adiabatic and the isothermal processes. And in this class, we will first start with a bit introduction about adiabatic and thermodynamic isothermal processes. And later, we will move on to some specific numerical problems that will be helpful for you to understand some basics of the thermodynamics. So I shall start with a brief introduction on adiabatic and isothermal processes. So you see, in thermodynamics, we specifically deal with gases. So in this case, we will try to figure out the specific conditions with the help of an ideal gas. So for ideal gas, you know the equation is PV is equal to nRT, where P, V, and T are pressure, volume, and temperature of the gas. N is the number of mole, and R is the molar gas constant. So if you see that when a gas is expanding, it is doing some work on the surroundings. Here, gas is the system, and the surroundings is the rest of the universe. Now, if the gas is expanding, it means it is doing some amount of work on the surroundings. On the contrary, when the gas is compressed, when compression of gas is taking place, the volume is actually decreased, which requires the surroundings is performing some work on the gas. So if a gas was in the volume V1 and it is expanding to V2, then V1 is less than V2. Because the gas is expanding, so the volume of the gas is increasing, so V2 must be greater than V1. So in this condition, it is doing some work on the surroundings. So if the gas or the system is doing some work on the surroundings, it is meant that the work done is negative in the era of thermodynamics. And in the reverse, on the contrary, if you see a gas is going from V1 to V2 by the mode of compression, so V1 if is greater than V2, then system is doing some work on the surroundings. System is performing some work on the surroundings. See, the surroundings also can do some amount of work on the system. So for V1 less than V2, when the volume of the gas is increasing, that is, it is expanding, the gas is doing some amount of work. When the gas is compressed, the surroundings is performing work on the gas. So then V2 is actually less than V1. Now, if the gas is thermally isolated from the surroundings, the process is said to be adiabatic. Previously, I have given you many examples like what are adiabatic systems. You have to remember this fact whenever I am saying that it is an adiabatic process. So, there is no heat exchange or there is thermal insulation between the system and the surroundings. Then Q is equal to 0. So for an adiabatic process, Q is equal to 0. According to the first law of thermodynamics, you know that delta U is equal to Q plus W. If I consider Q as 0 for an adiabatic process, then delta U becomes 0 plus W. So delta U is equal to W for an adiabatic process. So delta U is equal to WAD. This AD suffix turns up because of the adiabatic process. Now, since the temperature of the gas changes with the internal energy, that is the U, it follows that the adiabatic compression of a gas will cause it to warm up, while adiabatic expansion will result in cooling. So, why is it so? If you consider, if you say the temperature of the gas is changing, and it is also changing the internal energy. So the internal energy of the gas is increased. That is why in case of adiabatic compression, because when the gas is compressed, you see W adiabatic is minus P external into delta V. Let me just correct it over here. It is delta V. Okay. So W adiabatic is equal to minus P external into delta V. You see over here, if an adiabatic compression of a gas is going on, so delta V is equal to V2 minus V1. So gas was in its V1 volume. Now it is compressed to a V2 volume. So V2 is less than V1. That's why V2 minus V1 is less than 0. So that will be negative. That will be negative means this minus P external into delta V will be positive. That's why W adiabatic will also be positive. So the work done in adiabatic compression will be positive. And if you look carefully, delta U is equal to WAD. So if WAD is positive, delta U will also be positive. So the change in internal energy will be positive. So that means the increase in internal energy will happen. So if increase in internal energy is happening, that means the gas will eventually get warmed up. So it will eventually result in the gas getting heated up. The reverse will occur when adiabatic expansion will take place. For adiabatic expansion, V2 is greater than V1. So delta V will be greater than 0. If delta V is greater than 0, then W adiabatic will be less than 0. Because W adiabatic is minus of P external into delta V. Since delta V is greater than 0, so minus P external into delta V will be less than 0. Because the minus sign will remain. And since the minus sign will be remaining and the work done will be negative, so that means the gas will be cooled. Because if WAD is less than 0, it means delta U will also be less than 0. So the internal energy of the gas system will be decreased now, just opposite from the last case. So in this case, what will happen? The gas will eventually get cooled. So that's what it is written over here. Since the temperature of the gas changes with its internal energy, it follows that adiabatic compression of a gas will cause it to warm up, and the adiabatic expansion will result in cooling. So after giving you a brief introduction on this adiabatic compression internal energy change and the adiabatic expansion internal energy change, we'll come to a different state. So now consider a gas that is allowed to slowly escape from a vessel or a container which is immersed in a constant temperature bath. So if you consider a vessel over here which is closed and it has a gas which is at a constant temperature. A gas is here which is in a constant temperature bath. And now from an stopcock outlet like this, the gas will eventually escape. Now as the gas expands, it is doing some work on the surroundings. If it is doing some work on the surroundings, it means it is tend to cool. But the thermal gradient that results causes heat to pass into the gas from the surroundings to exactly compensate for the change, because it is in a isothermal situation. Isothermal means it is actually kept in a constant temperature bath, as it is written over here. So constant temperature means delta T is equal to 0. So if the temperature of the gas is not changing, because the thermal gradient that will result is causing some heat to pass into the gas from the surroundings. So exactly it will compensate the change or meet up the change. That's why it is called an isothermal expansion. Now, in an isothermal expansion, the internal energy will remain constant because you see delta T is actually here 0. If delta T is 0, so there is no change of thermal energy of the molecule, then the molecule's internal energy will also remain unchanged. So that will result in delta U is equal to 0. So for an isothermal process where the temperature is constant throughout the process, there is it is called delta U is equal to 0. So the isothermal energy in isothermal process, the internal energy remains always constant. So then in the first law of thermodynamics, which is delta U equal to Q plus W, we will put delta U as 0. So we'll end up getting Q plus W. The summation of Q plus W will be now 0. So for an isothermal process, Q is equal to minus of W. This equation is actually very significant. If you see, the mod value of Q will be now the mod value of W, because they are both same, but their signs are just the opposite. It is actually illustrates that the heat flow, that is Q, and the work done, that is W, are completely reverse to one another. They are actually balancing each other. So this is a heat flow and work done balance in case of isothermal expansion or compression. Now you see, no thermal insulation is actually perfect because truly adiabatic processes don't occur. However, heat flow does take time, so a compression or expansion that occurs more rapidly than the thermal equilibrium can be considered as an adiabatic process. Because in an adiabatic process, the condition is Q equal to 0. That means the system is thermally insulated completely from the surroundings or atmosphere. But that is not really attainable in reality. If you have ever used some hand pump to inflate a bicycle tire, suppose you are going somewhere by bicycle and your tire gets the pump gets off. Now you have to put the pump inside the barrel. Now, if you have noticed that if you are doing some work, if you are pushing some amount of gas from outside the tire or tube of the bicycle, you will see that the bottom of the pump will get quite warm because kind of you are doing some kind of work on the gas. Although a very small part, you can argue that this warming up may be due to friction, because if you are doing some amount of pushing some amount of gas from outside to the bicycle tire, because of friction some amount of warming can take place, but the mostly it will be result of a work that the surrounding is doing on the system, because from the surrounding you are pushing some amount of gas into the tire or the tube of the bicycle. So that's why it is kind of adiabatic compression. I am compressing the gas. So this adiabatic expansion and the contraction, the expansion and the compressions are especially important if you consider change in behavior of the atmosphere. So although we commonly think that the atmosphere is homogeneous because everywhere that is the same density, but in reality this is not the same, because you see somewhere someone is doing some cooking. So in case of cooking, the temperature is quite high. Somewhere there is fridge, so there the temperature is quite low. So that's why you see the heating and cooling are localized in some areas. Suppose you reside in a locality which is designated by here, and in locality if you see here a fridge is over here some amount of heat waves can carry out here. In case of you see there are multiple ACs which are installed inside a room. Here, some amount of burner or cooking is going on. So you see, in an atmosphere, though we consider it as homogeneous, it is not hot or cold at all the places, because of uneven heating and cooling are there in some specifically localized areas. Now, mixing and heat transfer between adjoining parcels of air does not occur rapidly. It takes some time. So, any commonly we considered the atmospheric phenomena can be considered not as fully adiabatic, but at least quasi-adiabatic. This quasi terms comes because it is not exactly the same what we are looking for, but to a bit amount of extent or small amount of extent, it can be considered as so. In atmospheric phenomena, no process is completely adiabatic, because fully adiabatic process means complete insulation, which is not attainable in reality. And also, you see, in a specific atmosphere, in all the places or all the areas, there is no temperature that is constant. Here, some amount of heating can go on, there, some amount of cooling can go on. And so, no process which is actually we are dealing with is completely adiabatic in nature. They can be considered as quasi adiabatic. Actually, so not fully adiabatic, but there are some characteristics for which we can call it as an adiabatic process. So, with this brief introduction in our mind or brain, that what is called the uh, thermally that isothermal process, or what is meant by the adiabatic process, we will move on to the next slide, where I will be teaching you about how to solve some numerical problems based on the understanding. So here I have taken two examples for easy understanding of numerical problems. The first one is going like this: a gas in a system has a constant pressure. Now the surroundings around the system lose 62 joules of heat and does 474 joules of work onto the gas. What is the internal energy of the system? I have repeatedly told you that whenever you will try to solve some problems on this thermodynamics, you have to remember about the sign convention and also the first law of thermodynamics equation. So whenever you will try to solve this kind of problems, you will write first the first law of thermodynamics equation, which is delta U is equal to Q plus W. And from the question, you will try to see what is given so that we can use those to solve the equation. It is saying the surroundings around the system lose 62 joules of heat. If the surroundings is losing 62 joules of heat, it means the system is taking that 62 joules of heat. And in my previous classes, I have told you, whenever heat is taken up by the system, the heat sign will be positive. And also, it is shown that it is doing some work onto the system. So the surroundings is performing 474 joules of work on the system. Work done by the system is termed as negative, and work done on the system is termed as positive. So here both Q and W are positive, because surroundings is losing 62 joules of heat, which is given to the system, and also surroundings is performing some work onto the system. That is why the internal energy also of the system will get increased. The system is getting heat and gets the work done on itself. So both Q and W are positive. So in this equation, if we put 62 joules in place of Q and 474 joules in place of W, we will end up getting delta U is equal to 536 joule. So the internal energy of the system will increase by 536 joule. That is the answer. In the next example, that is example 2 over here, it is saying a system has a constant value of volume, that is delta V is equal to 0, and the heat around the system increases by 45 joules. Now there are three questions that are asked over here. What is the sign for heat, that is Q for the system? What is delta U equal to, that is the change in internal energy? And what is the value of internal energy change in the system in joules? So one by one we will try to answer. Firstly, you see delta V is equal to 0. It is given over here. That is the system is undergoing no volume change. We have the work done W is equal to minus P delta V. Since delta V is equal to 0, so the multiplication of P and 0 will be also 0. So W, that is the work done, is 0 over here. So from the equation of first law of thermodynamics, we will have delta U is equal to Q only. So the answer of the second question we have got, that what is delta U equal to? Since delta V is equal to 0, because it is a constant volume process, so W is 0. So delta U is equal to Q. So we have got the answer that delta U will be equal to the heat change. Now, what is meant by Q over here? The internal energy is equal to the heat of the system, the change in internal energy. The question is saying that the heat around the system increases by 45 joule. Heat around the system. So the surrounding of the system's heat actually is getting increased. Now the surroundings heat is increasing by 45 joule because that amount of heat is relieved from the system. Since the system is going off 45 joules of heat, that means the system's heat will be decreased because the heat cannot be created, it cannot be destroyed. If the surroundings is experiencing some amount of heat, 45 joule is getting heated up, that means the system is losing that amount of heat. Therefore, the heat is taken away from the system. That makes the process as exothermic process. And then because the heat is taken away from the system, the sign of the heat will be negative for the system. So Q is equal to minus 45 joules. The value of the internal energy will also be negative. That is the negative value of the heat absorbed by the surroundings. The heat is taken away from the system Q. The system is over here, which is termed as S0. And it is the surrounding, that is SUR. The surroundings heat is actually getting increased by Q amount of heat, that is 45 joule. Where did this 45 joule or Q amount of heat is coming from? The answer is it is from the system. So from system, they are losing Q amount of heat. So the Q amount of heat is lost from the system. That means system is going away Q amount of heat. That makes the process exothermic. Now, what will be the value of internal energy? It will be the negative value of the heat that is absorbed by the surroundings. Because you know, when heat is taken away from the system, the sign of it will be negative. So delta U becomes negative of the heat that is absorbed by the surrounding, that is 45 joules. So the change of the internal energy of the system is minus 45 joules. So why this minus term is significant? If delta U is positive, it means the internal energy of the system is increased. Here, the internal energy of the system is getting decreased because Q amount of heat is going away from the system. In the expense of Q amount of heat, the delta U or the internal energy of the system will be dropped by 45 joules. The concept is quite clear over here. Between system and surroundings, whatever will be the amount of heat lost or gain by the system or surroundings will be compensated by the opposite one. Here I have come up with another example where all these of concepts will be very much easier for you to understand. The question is, find the amount of the work done on the surroundings when 1 liter of an ideal gas, initially its pressure was 10 atm, is allowed to expand at constant temperature to 10 liters by. Here also 3 kinds of different conditions are given. The first one is reducing the external pressure to 1 atmosphere in a single step, reducing the pressure first to 5 atmosphere and then to 1 atmosphere, and lastly allowing the gas to expand into an evacuated space or vacuum, so its total volume is 10 liter. So we will solve these problems one by one. Firstly, we'll see what are given to us. Here, in the first case, they are asking for the work done. Find the amount of work done. So if we come up with this answer over here, we need the W. In this case, we will see that we are dealing with delta V, because 1 liter of a gas is overtaken over here. That is V1. V1 is 1 liter. And finally, it will be expand at constant temperature to 10 liters. That is V2 is equal to 10 liter. Against a constant pressure of 10 atmosphere, and initially we reduce the external pressure to 1 atmosphere in a single step. So initially we will have P1 is equal to 10 atmosphere. And P2 will be different in the other cases. What will be P2? So if we can solve the problem, we will start solving with A. So in this case, we will also deal with delta V. Now for this V2, V2 is actually 10 liter. Now if we calculate delta V, which is V2 minus V1, so 10 minus 1 liter, which is 9 liters. So 9 liters is delta V. So for path A, if we calculate W, W is minus of P external into delta V. So minus of P external, if you see over here, in case of A, they are saying the reducing the external pressure to 1 atmosphere. So in this case, P2 or P external will be 1 atmosphere. Also, we have delta V calculated from the last equation, which is 9 liter. So I guess you are guessing how we can go out or carry out this kind of numerical problems by dealing with each of the every term that is given to us. And now with these simplified equations, W is equal to minus P external delta V, we will calculate the work done. So here we see W is equal to minus P external into delta V. P external is equal to 1 atmosphere, which is written over here, because they are decreasing the external pressure to 1 atmosphere from 10 atmosphere. So 10 atmosphere is not required over here. and we are having delta V as 9 liter. So we'll end up having minus of 9 liter atmosphere of water. If you know that 1 liter atmosphere corresponds to around 101 joule. So 9 liter atmosphere will correspond to minus of 909 joule. You can also express it in terms of kilojoule or kilocalorie. But for this instance only, we will deal with the atmosphere and joule because it will be easier to express these terms. Now we will come to question number B. So in case of question number B, we have actually two paths. If you see over here carefully, they are reducing the P external to 5 atmosphere and then reducing it to 1 atmosphere. So we have two paths, and separately in each stage, we will calculate the P external and the delta V. So in this case, W, for the last case, we had only one final external pressure and one final volume. That's why there was only one term. But here, the entire process is actually segregated between 2 to 3 procedures. Like from 10 atmosphere of pressure, it is going to 5 atmosphere pressure first, and then from 5 atmosphere of pressure, it is going to 1 atmosphere of pressure. So here we have this P2 and P1. So we are having this minus of P external into delta V of summation. So we have two processes. Summations means we have 1 to 2 different pressure, external pressure and delta V. Now for the first case, the reducing the P is actually P2 is 5 atmosphere. So P2 will be 5 atmosphere in first case. And the second case, P2 will be 1 atmosphere. Now we have to calculate what are the delta V's over here. So firstly, the V1, it was in 1 liter. Now V1, now what will be the final volume of the first case? Here we are having a P2. And here we are having V2 and V1. And for the next case, we have a P3. And the volume change is V3 minus V2. For the first case, we are getting that P2 is equal to 5 atmosphere, which is written over here. So P2 is 5. And V2, that is the final volume that we have to calculate. Now, for how we will calculate V2 and V1, here comes the Boyle's law. That is PV is equal to constant. From Boyle's law, we have to calculate what will be the volume, that is V2 over here. This V2 will not be considered because you see over here, this V2 was on the final case. But here the process is different. They are reducing P first to 5 atmosphere and then to 1 atmosphere. So in this case, what will be the V2? Firstly, we will have that the final volume of the gas, and we have the initial volume of the gas. Initial volume of the gas, 1 liter was there. And we had a pressure P1 of 10 atmosphere. Now we have a P2 or the final gas pressure as 5 atmosphere. So then what will be the gas volume, which is X? By solving this equation, we will see x is equal to 2. So we will put 2 over here in case of V2, which is V2 minus V1. V1 was this one, 1. Likewise, we will calculate P3. In case of P3, you see finally it will be 1 atmosphere. So P3 is 1. Now again we have to calculate V3 minus V2. So from V2 we have calculated V2 is 2. And what will be the final volume? The final volume is written over here, that is 10 liters. So 10 will be here. So if we solve this, we'll get this 5 into 1, that is 5, and 10 minus 2 is 8. So 8 plus 5 is equal to 13. And since we have a minus over here, so we'll have minus 13 in liter atmosphere. If you need, if you can convert it to joules, but here let it remain in this case only. So for the first scenario, that is A, we are having a work done that is minus of 9 liter atmosphere. And in the second case, we are having a work done which is minus 13 liter atmosphere. If you have a closer look at it, you will see the ideal gas volume was 1 liter, and finally it was pressed to 1 atmosphere from 10 atmosphere. So in the case of A, path A, it was from 10 to 1 atmosphere. In case of path B, from 10 atmosphere, it is going to 5 atmosphere first, and then it is finally going to 1 atmosphere. So we have two paths. We have a gas which is in a G1 state, which is going ultimately to a G2 state. So from G1 to G2, we have two paths. One is path A and another is path B. In path A, G1 to G2 is accompanied by a direct change in pressure from 10 atmosphere to 1 atmosphere. So it was firstly in a 10 atmosphere phase. Now it is in a 1 atmosphere phase. Now in the second case, that is path B, it is having a halt at a G prime position. In G prime position, you see from 10 atmosphere, it is taking a halt at 5 atmosphere and then finally going to the ultimately same destination, that is 5 atmosphere to 1 atmosphere. So if you see over here, it is dependent upon the path. So in work done in case of path A is minus 9 liter atmosphere. But work done in case of path B is minus 13 liter atmosphere. So that actually shows that work done is not a state function. Work done is not a state function. It depends on the path, because state functions are those where the change amount of the parameter does not depend on the path that is taking or route that is involved. In case of these cases, from G1 to G2, we have path A and path B. In case of path A, from 10 atmosphere to 1 atmosphere, we are going by a single concerted step. But in the second case, that is path B, we are going in a stepwise manner. Firstly, from 10 atmosphere to 5 atmosphere, and then from 5 to 1 atmosphere. In case of A, the work done is minus 9 liter atmosphere. In case of path B, the work done is minus 13 liter atmosphere. The amount of change is around 4 liter atmosphere. So the work done by the system on the surroundings is more when we are taking more halts. So if you consider, like if you can similarly devise some problems where you can say from 10 atmosphere to 1 atmosphere, we will take more halts. From 10 to 1, we can first go from 10 to 8. Then we will go from 8 to 6. Then we will go from 6 to 3. And finally, we will go from 3 to 1. In this case also, you will see the work done will be much higher. So depending upon the path or the route that is taken up by the system, we will see the amount of work will be changing. So in case of path A, we have calculated it as minus 9 liter atmosphere. In case of path B, we have seen that this minus 13 liter atmosphere. Now we will come to path C. So I will summarize over here. In case of path A, the amount of work done was 9 liter atmosphere. In case of path B, it is minus 13 liter atmosphere. Now we will calculate for path C. What is the work done for path C? So in case of path C, it is allowing the gas to expand into an evacuated space or vacuum. Its total volume will be 10 liters. For path C, if it is going to an evacuated space, that means the piston that is was upon the gas was lifted up. There was a gas upon which there was a piston which was producing some external pressure on the gas. Now the gas is released because all the waste from the pistons is now removed. So the gas expands to 10 liter against zero external pressure. Now the gas is the P external is zero, but the volume against which it will be released will be 10 liter. So V2 will be 10 liter. Now if we come down to the equation of work done will be minus P external into delta V. So if any one of these P external and delta V parameters is equal to 0, we need not to calculate or worry about the other term. Here also, since P external is equal to 0, W will be equal to 0. So in this case, there is no work done because there is no force to oppose the expansion. So we have to always remember this very important situation, that work done in against a zero external pressure will always be 0. So work done against zero external pressure will be equal to 0. The physical meaning of this, that is, there is no work done by the system because it is working against a net zero force. There is nothing to oppose the expansion of the gas. That's why against a zero external pressure, the work done will be equal to 0. So here in case of C, the amount of work done is 0 liter atmosphere. So we have three scenarios in this question. First one is the reducing the external pressure directly to 1 atmosphere in a single concerted step. Second scenario was reducing the P first to a constant to 5 atmosphere and then ultimately to 1 atmosphere. And lastly, allowing the gas to expand into an evacuated space, so its total volume is 10 liter. So in all the cases, we have calculated what are the work done in this case, and we'll have seen that whenever we are splitting the steps in multiple steps, like in this case, we did not go to the 1 atmosphere step in a single step. We took a halt in between, which is 5 atmosphere, and then went to the 1 atmosphere step. We saw that the work done was quite higher by the system. That actually shows that W is not a state function. Because it depends upon the pathway that is involved. The route taken in between actually determines what will be the value of W or the work done. So here I have come up with a very brief questions for you guys to understand about the thermodynamics. It is kind of an overview, you can also say, of the entire chapter, of the part of the chapter that we have learned over here. So we have, so one by one we will check all the things. Firstly, we will start with the question number 1. So what are the limitations of the first law of thermodynamics? So in first law of thermodynamics, we have also seen some very good important points. The relationship between internal energy, Q, that is the heat involved, and W, that is the work done. But a single law cannot afford or cannot actually produce all the experimental results. That's why the first law also has some limitations or drawbacks. Firstly, it does not tell us about the direction of the flow of heat. It tells us about the heat flow, but it does not give us any idea about in which direction the heat is going or flowing. And secondly, it does not explain why heat cannot be spontaneously converted into work. So these are two main limitations of the first law of thermodynamics. Secondly, what is the mathematical form of the first law of thermodynamics? We have dq is equal to dv plus dw, but dw is equal to pdv. So dq is equal to dv plus pdv. So dq is the heat absorbed by the system, dv is the internal energy of the system, and dw is the work done by the system. P is the pressure and dv is the change in volume. Also, you can see that delta U is equal to Q plus W, which is also the mathematical form of the first law of thermodynamics. Take the first law of thermodynamics, which you will find in every textbook, but because of your ease of understanding, I have written over here. The first law states that the energy entering the system in the form of heat is equal to the sum of increase in the system's internal energy and the energy leaving the system in the form of work done by the system on its surroundings. What are the applications of the first law of thermodynamics? For first law of thermodynamics, we can apply it on some different processes. First one is the isobaric process. In case of isobaric process, the pressure remains constant. So delta P is equal to 0. So in case of isobaric process, the pressure is equal to delta change of the pressure will be equal to 0. So there are several other kind of processes also. Here we can see that isobaric, isochoric, there will be some different kind of equations or conditions. So we are having the isobaric process where it will be constant pressure. Then we have an adiabatic process. For adiabatic process, I have told you a number of times, that is Q is equal to 0. In case of isochoric process, which is delta V equal to 0. For isochoric process, delta V equal to 0. So the work done will also be 0. Because work done is minus of P external into delta V. So for free expansion or for isochoric processes, W is equal to 0. You have to remember this kind of questions come into an exam. So here we can see where the work done will eventually become 0. There are two very different scenarios where work done will be 0. First one is the isochoric process, where the change of the volume of the gas is 0. Then W will be 0. And also in case of free expansion, that is expansion against nothing, there will be no force to oppose the expansion, or expansion in vacuum, or expansion in an evacuated space. So in all the cases, W will be equal to 0. In case of isothermal processes, delta U will be 0. Because there will be no temperature change of the system. That means there will be no internal energy change. In case of isochoric processes, we see that is in case of isochoric process, delta V will be 0, so W will be 0. So that means delta, in case of delta U is equal to W. So W will be 0. So delta U will be Q. In case of adiabatic process, Q will be 0. In case of isobaric process, that is delta V, that will be delta P will be 0. So there will be different applications of the first law of thermodynamics. We'll come to the next question. It is the first law of thermodynamics, the law of conservation of mass or energy. Which one? In case of first law of thermodynamics, it is the law of conservation of energy, not the law of conservation of mass. Define an irreversible process. So in a irreversible process is in which the system cannot be retracted to its original state is called an irreversible process. So we have two states, A and B. If A can go to B and B can eventually come back to A, it will be called an reversible process. But if A cannot be, B cannot retract or revert back to A, it will be called an irreversible process. So here there is the denomination of the reversible process. A process is said to be reversible when the various stages of an operation to which it is subjected can be traversed back in the opposite direction in such a manner that a substance passes through the exactly same conditions in every step in the reverse process as in the direct process. So from A to B, if there were some infinite number of stages, so from B to A, there will be infinite number of stages too to revert back. And what is an isolated system? A system is said to be an open system if it can exchange both energy and matter with surroundings. And if it's not so, if it can't exchange energy and matter with surroundings, it will be called an isolated system. So with this, we'll finish our today's discussion. If you have any question or any query, you can go ahead and ask.